So we're in the gas power cycles. There's 3 gas power cycles you need to become familiar with. The Otto cycle, the diesel cycle, and the Brayton cycle. Air standard analysis, it's a set of assumptions. I'm going to go over those in the next slide. But those set of assumptions apply to the Otto, to the diesel, and to the Brayton cycle. And they make it much more doable, calculations doable. What is the application of the Otto cycle? How many people buy gasoline and then drive a vehicle? Well, there you go, right? It's simulating what is happening in your gasoline engine of an automobile or of a lawnmower or of a weed eater or a lot of other components run off gasoline. What about a diesel? Well, if you have a vehicle that runs on diesel fuel, it's a diesel cycle. You own a pickup truck or a heavy truck that drives, on the road. You have a commercial driver's license. Often they're diesel engines. And then what about the Brayton? Where do we see those? What is that simulating? It's simulating a bunch of stuff. Stationary gas power plant to make electricity where it burns natural gas. Or it's simulating a jet engine on an aircraft. Or a helicopter jet engine. That's how the propulsion systems in helicopters work, as well as large ships. So what is the air standard analysis? Well, it's too complicated to track the change of the hydrocarbon fuel, and some of the oxygen goes away and some carbon dioxide and some water vapor appear. We just assume it's always air, before and after combustion. And it always behaves as an ideal gas. That's a pretty good assumption anyway. That's not a stretch. And then the combustion is a complicated process, so we replace it in the analysis by simply a heat transfer. You say there's a combustion chamber. Well, just replace it by a heat exchanger or a heat transfer into the working fluid in combustion. The exhaust is a complicated process, so what we do is just sort of close the loop or close the cycle, and it's a heat transfer typically to reject heat to the ambient atmosphere. And we assume everything's frictionless. It's internally reversible. Everything's internally reversible for all the processes. So what happens if they add the word cold in front of air standard analysis? Well, it's everything with the air standard analysis with the additional assumption we'll use constant specific heats evaluated at 25 C, which is close enough, not exactly, to 300 Kelvin. So 25 C or 298 Kelvin. These are some equations that we'll make heavy use of in this chapter. What are they? Well, ideal gas, constant K, constant specific heat, undergoing isentropic processes. And this is how pressure changes as volume changes, how temperature changes as volume changes, and how temperature changes as pressure changes. So we use this one especially, and that one especially in the Otto and diesel cycle, and this one especially in the Brayton cycle. That's just the type of analysis we need to carry out. So the Otto cycle is named after this person who lived during these years, 1832 to 1891, Nicholas Otto. He was a German engineer. You can see that they honored him with a postage stamp, and this is a big flywheel connected to piston going back and forth in some engine. So that's the Otto cycle. We'll talk a little bit more about it. Here's the diesel. It's named after a man whose last name was Diesel, Rudolf Diesel, German engineer. These are the years that he lived. And they even honored him by some year. I don't know what year this postage stamp was issued in Germany, but by a postage stamp. What about Brayton? Well, George Brayton is an American. Every now and then you'll find an American that contributed in the science of thermodynamics. And these are the years that he lived. And where's his postage stamp? Hasn't been issued yet. But the Brayton cycle is very diverse. It's very diverse. It does describe how a jet engine, and especially if you put on the back of it a nozzle to kick it out the exhaust gases or products at high speed, that you get forward thrust from fluid mechanics. But if you have a ship and you want to propel it, if you went on a cruise ship, you went down to Galveston, got on a cruise ship, went out, whatever, floated around for a week, that's all gas turbine engines driving those ships. Also, helicopters, as I mentioned, that's the drive. So if you've been in the military, you know that. How about tanks, the Abrams M1? That's all a gas turbine engine. It's not pistons reciprocating. Okay? They used to be piston cylinder reciprocating diesel engines and a lot of those, but they've been replaced. Why? Lower weight for higher power output. So the package can produce a lot of power for a little bit of weight. Well, let's talk about closing the loop here on the Brayton cycle. So we have a compressor, combustor, turbine, and this would typically go out the stack, exhaust. But to close the loop, you put a heat exchanger, and now you have a cycle. There's our cycle. So the only place that there's heat transfer into the system is in the combustor, and there's heat transfer out of the system is in this imaginary heat exchanger to close the loop. There's typically a shaft that connects the turbine back to the compressor, and some of the output, shaft output of that turbine drives the compressor. It takes a lot of work to boost the pressure of an ideal gas going through the compressor. Where does it come from? From the turbine. And the excess can drive an electric generator to make electricity and sell it. Okay? So that's the general idea of the Brayton cycle. So let's try and put these all in comparison. So for Otto, for a diesel, and for a Brayton, I would like to put them on a pressure, a volume diagram, a PV diagram. So think of a piston in a cylinder. So this is the cylinder, maybe the piston starts here, and you end up compressing to a smaller volume. So it starts at state 1, ends at state 2. You could think about the volume at 1 or the specific volume at 1. For the trapped amount of gas isn't changing in the closed system trapped in that piston cylinder, right? The Otto cycle, you have to remember, it's a closed system analysis that we apply. It's in a piston cylinder as the gas gets compressed and expands and heated and that. So from 1 to 2, it goes to volume 2, which is equal to 1 over the compression ratio, R, times the volume 1. Or by definition, the compression ratio is the volume 1 divided by volume 2, either total volume or per unit mass, either way. Okay. So a lot of times we could start and visualize. There's kind of lining up here, state 1 at low pressure, high specific volume. And then there's state 2 kind of lining up there. And we typically have a nice kind of curve upward. It's not a straight line from state 1 to state 2. At the end of the compression stroke, it's very hot. It's very high pressure. Why is it hot? Was there heat transfer? Was there any heat? No, it's adiabatic compression, and it's reversible, hence it's isotropic compression. Then why did the temperature go up? There must have been a heat transfer. No, that's what you learned in this class. You can have temperature change without heat transfer. And you can have a lot of heat transfer sometimes with no temperature change. So anyway, it comes from all that compression work. So now you're at 2. Typically we have a combustion. We model that as constant volume, heat addition to state 3. And then we go through expansion so that we get down to state 4, and then we can do constant volume heat rejection. So the heat transfer comes in during the constant volume heating from 2 to 3 and goes out. Some of it goes out. And the constant volume cooling from 4 to 1. It's adiabatic. Sometimes we draw it with a dashed line like that to indicate, hey, it's well insulated. There's no heat transfer from 1 to 2 or from 3 down to 4. So if you wanted to, you finish this out. You put this right here, the piston at state 3, but now it's hot. Why? Because between 2 and 3, at constant volume, it was heated. That's the highest temperature of the cycle. And then you expand it back out to state 4. Then you cool it at constant volume from 4 back to 1. All right. What is the parameter that characterizes it? The compression ratio, R. So again, what is that compression ratio? The large volume, if you work with these things, you talk about the pistons at bottom dead center, and then it goes to top dead center, and then that's the smallest volume. So V1 divided by V2 is the compression ratio. Let's put that also on a temperature entropy diagram. Well, from 1 to 2, it's isentropic. Then 2 to 3, you're going along a line of constant volume, and you're heating it. And then from 3 to 4, you're coming down, you're expanding it isentropically, and then constant volume, heat rejection from 4 back to 1. So that's what the cycle looks like, both on a TS as well as a PV diagram. Let's do the diesel. Oh, for one other thing. For practical application, this is used to simulate our gasoline engines. Okay. What is a typical compression ratio for many gasoline engines? How many people? Do you own one? What's the compression ratio? About 10, 11, 9.5, somewhere in there. So if you wanted to pick a number, just say compression ratio about 10. Now we're going to talk about a diesel. Now the diesel is a piston cylinder sliding, going back and forth compression. But what's the typical compression ratio on a diesel? Who owns a diesel engine? Anybody own a diesel engine? Nobody? The whole group? Right? Not in a car or in a truck? How many would say the clacking noise of a diesel exceeds the clacking noise of a gasoline engine? They're getting rid of that clacking noise. They've done a lot to improve it. But anyway, the compression ratio on a diesel engine often is about 20 to 1. So it compresses a lot smaller volume. Smaller volume. So if you wanted to think about it, you could, I don't want to redo all of it, but you would compress it to a smaller volume, put that piston even smaller, closer, right? So it's 20 to 1 compression ratio. The pressure and the temperature even go up higher, don't they? So the start at state 1 goes to a smaller volume down here at state 2. But then it's followed by constant pressure heat addition. In a diesel engine, let me back up a little bit. In a gasoline engine, when you ingest air into the cylinder, piston cylinder, is the fuel mixed with the air? It is. When did it get mixed in the air? In the intake manifold. Or with the fuel injector right before it goes into the cylinder. Somewhere in the intake system, okay? Used to be in the carburetor. You probably don't even know what a carburetor looks like. Huh? Who owns a vehicle with a carburetor? 1, 2. Oh, there is a few. Yeah. Do you still drive it? Or is it on a display case somewhere, a museum piece? It's getting to be a museum piece. But anyway, fuel injectors are the way you mix the air and the fuel, and you spray it in typically at the intake manifold. It's atmospheric pressure. It's easy done. Then you're compressing in that compression stroke in a gasoline engine. It's the air-fuel mixture that's being compressed. Now, what about a diesel? You have a fuel injector, but you don't inject the fuel in the air mix before it gets ingested into the cylinder, do you? What's drawn into the cylinder is just pure air. Then it goes into the compression stroke. There's no fuel mix. When does the fuel show up? When the fuel injector sprays it into that high pressure, high temperature combustion chamber. So it's constant pressure heat addition, because as it's starting to spray the fuel in, it's burning, it's starting to expand and go into a power stroke. It's pushing down on the face of that piston. So in the modeling, it's not perfectly constant pressure, but we approximate to be constant pressure heat addition. Constant pressure heat addition. Then somehow you cut off the fuel, and it still expands, but now it's adiabatic. And there's the cycle from 1 to 2 to 3 to 4. So the heat addition is at constant pressure. What was it for the Otto? Constant volume. Constant volume. The volume was constant, not the pressure constant. Which one has a spark plug? The Otto, the gasoline. And the spark fires, and in the Otto cycle analysis, combustion happens really fast. All at top dead center, boom, the pressure and the temperature go way up. Constant volume heat addition. All right. Now, let's take a look at it on a TS diagram for the diesel cycle. Well, it's straight up 1 to 2, but then you have a constant pressure heat addition from 2 to 3, and then constant your isentropic expansion still from 3 to 4, and then back down to 1. All right. That's pretty complicated. What I'd like to do is just try and, I don't know if this will work, I'm going to try and shrink these down. Just sort of shrink them down and kind of tuck them there so you can still see them. And now I want to talk about the Brayton cycle. All on the same diagram, because if you get it all these three cycles straight in your mind, I think the analysis is easy. You have all the tools to analyze them. Yes, sir?
Is the diesel cycle also closed?
Yes. It's a closed system as well. So it's a trapped. That's a perfect lead-in for my next observation. This is closed. Guess what? Brayton is open. You have those 4 components. Remind me again of those 4 components. A compressor, a combustor, a turbine, and some heat exchanger to close it out, some imaginary heat exchanger. Okay, we'll start with state 1 being on the inlet to the combustor, state 2 inlet to the compressor, inlet to the combustor, inlet to the turbine, inlet to that heat exchanger. So here you would do a open system analysis for the control volume around each of those 4 components. Around the compressor, then control volume analysis around the combustor, around the turbine, and around the heat exchanger. What was the difference? We had a trapped amount of gas in the Otto and diesel that just went through different, change volume by being compressed, heat it up, expand it, cool it. Here, it's a different way of analyzing. The flow goes through each of those components in a cycle. So let's do this. What happens on a PV diagram as I go from state 1 to state 2? Well, the compressor boosts the pressure, doesn't it? So the pressure at 2 is high. Does the pressure change as you go through the heat exchanger known as the combustor? Or is the pressure 2 equal to pressure 3? Are they the same pressure, or is there a pressure increase as I go through the combustor? Well, what's happening in combustor? It basically has air coming through, and it's a little complicated, but you throw in the fuel, and you have a spark plug always click, 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 or once the fireball is going, it doesn't need a click, click, click spark plug, and it's just burning, continuously burning. Then it goes out. All right? So fuel with the air, and somehow it got burning, and it's staying burning, okay? Is there a mechanism to increase the pressure from the inlet state 2 to the outlet state 3 of a combustor? Read my body language. No, right? There's none. So the pressure at 2 is equal to pressure at 3. That's our high pressure. What about the pressure at 4 versus pressure at 1? Same pressure. So pressure at 4 equal to pressure at 1. That's our low pressure. So really think about, on the Brayton cycle, 2 distinct pressures, high and low. That'll help you a lot. Now we're going to take and compress it and go like that up to, from 1 to 2, going through, what happens? Going through the compressor. Now you go through the combustor, it's going to heat it up, the pressure stays the same. There's state 3 on a PV diagram. Now I need to go back down to state 4, and then 4 back to 1. There's our Brayton cycle on a PV diagram. Yes, sir?
I know it might just be the way it looks, but is the specific volume at 1 equal to the
No.
specific volume at
It's just coincidence the way I drew it, sorry. V1 is not equal to V3. The specific volume at 1 is not specific volume at 3. Now I tried to leave enough room. Let's tuck it in. Temperature entropy diagram. Okay, temperature entropy diagram. From 1 to 2, it's isentropic compression through that compressor. 2 to 3, constant pressure. Heat addition, so it's going to be going up, constant pressure, to 3. What about 3 to 4? Isentropic, and then constant pressure, 4 back to 1. So we have in our mind the mechanisms. Oh, it's closed system analysis for Otto, closed for Diesel, open for Brayton, and we have these diagrams to help guide us. We also have the compression ratio for the Otto cycle. We have the compression ratio for the Diesel, as well as the cutoff ratio. What's the cutoff ratio in the Diesel? Well, it's when the fuel cuts off and you stop that constant pressure heat addition. It's V3 divided by V2. That's the cutoff ratio. How about for the Brayton cycle? Well, we don't talk about a compression ratio. We talk about a pressure ratio. A pressure ratio. The difference between the P low and the P high. So it's an open system analysis, and they just quote P2 divided by P1, or P high divided by P low. That'll be a pressure ratio. Professor, you said the Otto cycle compression ratio is around 10. You said the Diesel compression ratio is around 20. What is the pressure ratio for, I don't know, a gas turbine? Could be 8, 10, 12, 16. They try to push it up into even to the low 20s because that is great for performance. But it's really hard to do a good job of designing and building and getting to run for a long time reliably a centrifugal type of compressor. I think I showed you a video of having the stators and rotors rotating like that in a compressor, and that's just a challenge. But the higher that pressure ratio is, the better it's going to be for performance. So what I need to do is to analyze a system like this, I need to write the first law of thermodynamics. I need to make some room here, so I'm going to do this. I need to write the first law of thermodynamics for each of the processes in the 4-process cycle for the Otto. So for 1 to 2, we have Q 1 to 2 minus the work 1 to 2 is equal to U2 minus U1. Does that equation make sense to you? And then Q 2 to 3 minus work 2 to 3 is equal to U3 minus U2. And then Q 3 to 4 minus the work 3 to 4 equal to U4 minus U3. And then Q 4 to 1 minus the work 4 to 1 equal to U1 minus U4. So that's the first law of thermodynamics for each of those closed system processes in the Otto cycle. Is it any different for the Diesel cycle, or do they have the same basic equations? They're the same. So what we'll do is we'll write them over here for the Diesel cycle instead of that. Now what we'll do is we'll say for each of these, which terms are 0? Which terms are equal to 0? So for the process 1 to 2, is Q 1 to 2 0 or work 1 to 2 0? Q 1 to 2 is 0. Why is Q 1 to 2 0? It's adiabatic compression. Now thinking along, how about 3 to 4? Adiabatic expansion, isn't it? So those two Q's are 0. All right. Are any W's equal to 0? Is W 1 to 2 equal to 0, 2 to 3, 3 to 4, or 4 to 1 equal to 0 for the Otto? Constant volume. Anything that's constant volume, there's no boundary work, is it? So 2 to 3 is constant volume, and 4 to 1 is constant volume. So it really makes the analysis a lot easier when you observe that. Now, before I talk about putting properties in a table and making these calculations, let's walk through and think about this. Work 1 to 2. we have the traditional sign conventions used for each of these four processes. Is that work 1 to 2 a positive work, meaning the gas is being compressed? Or is it, a positive work, meaning the gas is expanding and doing boundary work, pushing back the piston? Or is it negative? This work 1 to 2 in our calculations needs to be negative, right? How about the Q 2 to 3? Is that positive in? Or is it a negative in? Q 2 to 3. This is positive. How about work 3 to 4? Is that positive out or negative out? What is it? 3 to 4, is that work? So I'm going to calculate a very positive quantity for work 3 to 4. How about Q 4 to 1? Negative. So kind of get in your mind, yeah, that's a positive and that's a negative, so we avoid errors. Let's do the same thing for the Q's on the diesel cycle. Is Q 1 to 2 equal to 0? Diesel cycle. Here's state 1, there's state 2, it's just a compression stroke. Yeah. How about Q 2 to 3? Positive. That's positive because it's a constant pressure heat addition. How about 3 to 4? 0, it's adiabatic expansion. How about 4 to 1? Negative because it's heat rejection out of the cycle. Let's do the works. Work 1 to 2. Negative because it's compression. Work 2 to 3. 0 or positive? Positive. Notice the difference. Here, can you compare the auto? There's not too many differences between the auto and the diesel, but look at that work, 2 to 3. It was constant volume heating in the auto, constant pressure heat addition in the diesel. All right, let's continue on. Work 3 to 4, positive, negative, 0? Positive. And work 4 to 1? 0. Finally, we got a 0 there. So there you go. That helps a lot, I think. Now, sometimes this equation right here for the process 2 to 3, because it's a constant pressure heat addition, you can rewrite it. Can you take that work 2 to 3 and say that's the integral PdV? P is constant, pull it outside the integral. Move it over to the U side, and you can get an equation that says Q 2 to 3 is equal to H3 minus H2. What? How many people, yeah, that makes sense. Does it make sense? Yeah. And so sometimes what will happen is you'll see some student that will say, like, I don't understand, how come, professor, sometimes there's U's, sometimes there's H's, I get all confused. Go slow. When you have a closed system, first law, it's a change in internal energy U. But this has a constant boundary work. So for the diesel cycle, for 2 to 3, you can write the amount of heat added is equal to the change in the enthalpy. All right. Okay. Let's do this. Let's make a schematic of the first law analysis, but we don't do it for a process, we do it for each of the components, don't we, for the Brayton cycle. So let's kind of write it here for the combustor, then the compressor. Compressor, just C, the combustor. We'll write it also for the turbine, just a T, and the heat exchangers. So what does the first law of thermodynamics look like for that open system around the compressor? You do a little bit of work. Let me do it on the side. Rate of change of energy in the control volume with respect to time is equal to the rate at which it flows in with heat minus the rate at which it flows out with shaft work, plus it's flowing in with its enthalpy in and out with its enthalpy out on neglect changes of kinetic potential energy. Does that equation look good? Are we doing any transient? No, it's steady state. We'll divide everything by m dot. And so then this becomes a lowercase q. This is a lowercase wcv. And then on the other side of the equation, we'll put an h2 minus h1. Did I do the algebra correctly? Does it look okay? Looks good? All right. I didn't want to jump too fast, but there you go. Now, that little W for the CV kind of gets a little cumbersome, but that is shaft work. Isn't this shaft power? Think of shaft power when you see that coming out of the control volume, right? So what I'm going to do is I'm going to say I need to write this equation not only for the compressor, but I need to write it for the combustor. Q, the combustor, minus the work combustor equal to the change in the enthalpy, H3 minus H2. And then for the turbine, Q of the turbine minus the work turbine equal to H4 minus H3. And then for the heat exchanger, Q heat exchanger minus W, work heat exchanger equal to H1 minus H4. Did I make any errors? Does it look okay? All right. Let's take a look at which of these Q's for which of these components is 0. For the compressor, is there any heat transfer? No. So we can take that term and strike it, can't we? It's 0. It's adiabatic compression, isentropic compression. How about in the combustor? There's a lot positive large heat transfer into the working fluid in the combustor. Make sense? How about for the turbine? QT. 0. And then what about Q in the heat exchanger? It's negative. It's negative. Negative. All right, let's do the works. The work, remember that shaft work coming across the boundary and encircling the compressor. Is that 0, negative, or positive? Negative. How about for the combustor? I get that question all the time. They say, Professor, why isn't there work with the combustor? I say, where's the shaft going in or out of the combustor? There is no shaft going in or out of the combustor, is there? So that is 0, isn't it? How about the work turbine? Positive out. And how about the work heat exchanger? That's 0. I know that this board is really full. I'm going to scoot down a little bit. But now that we have a plan for how to get the W's and that, what you do for each one of these is think, what is Q net for the Otto cycle? Isn't it Q1 to 2 plus Q2 to 3 plus Q3 to 4 plus Q4 to 1? And even though 2 of those terms are 0, that's still a good equation. What is W net? The network is just W1 to 2 plus W2 to 3 plus W3 to 4 plus W4 to 1, right? Even though 2 of those W's are 0, that's true. And when you're doing these calculations, should these two be equal? They are the same. Please check, 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 and have you solved some problems and then checked them and said, oh, I'll go find my error. I got an error if they're not the same. The metric of interest is the thermal efficiency for the Otto. What would that be? Would it be the net work out divided by the heat in? Where is the heat into the cycle? Q, 2, 3. That's the only heat in. And there's a mean effective pressure. I'm not a big fan of this metric. Maybe they'll make a big deal of it when they do Thermo 2 next semester with you. But it's the work net of the cycle divided by the displacement volume. Well, what's that? It's the difference between the initial volume, V1, and the final volume, V2. So it's V1 minus V2. That's the displacement volume. How many people, have an engine in their car and they know, oh, it's a 2.2 liter or a 5 liter or 350 cubic inch or whatever size the engine is. What are you quoting there? It's the displacement volume, isn't it? Isn't that the displacement volume? So if, let's say it's an 8 liter, just to make the math easy, and I have 8 cylinders, that means each cylinder has 1 liter's displacement volume. So you just take the total, let's say 5 liter engine, oh, it's 5 liters and 8 cylinders. 5 divided by 8, whatever that gives you, is how many liters per cylinder. That's the displacement volume. That's the swept volume as it moves from bottom dead to top dead center. That's what that is. Okay, so that's a metric that you can compute the mean effective pressure. Usually you like a high mean effective pressure for a lot of work out for the same displacement volume. But again, the thermal efficiency is good. Now you could do the same thing for the diesel. Is there any difference? It's all the same for the diesel and the Otto cycle. It's just some of those Q's and some of those W's are changed. What about for the Brayton cycle? You could talk about the Q net for the cycle. That's the Q that's in the compressor, which is 0, plus Q combustor, plus Q of the turbine, which is 0, plus Q heat exchanger, right? And then you could talk about work net. Work net, you have, let me just put the non-zero terms. It'll be the work, the compressor, which is negative, plus the work of the turbine, which is positive. And then you could talk about the thermal efficiency. It would be work net divided by Q in. The only place there's Q in is in the combustor. So you could talk about that as a metric, the thermal efficiency. There's another one for this cycle. It's the BWR. Saw it in the vapor power cycles, in the Rankine cycle, didn't we? What is the BWR? Back work ratio. So there's typically a shaft. This turbine and the compressor are connected in a shaft. And some of the power out of that turbine has to go back and feed the compressor. If you're making electricity, the surplus goes out to run the generator. But the back work ratio is the work that goes back to feed the compressor. You might want to put a negative sign on it to get rid of the negative sign, divided by the work that the turbine produced. Okay. Finally, I'm trying to get to this, is make a table of all your states and then figure out 1, 2, I got to scoot down a little bit more, 3, 4, what properties would be of interest? Probably pressure, temperature, maybe it's in kilopascal, maybe it's in Kelvin, maybe the specific volume, maybe the internal energy. It's always an ideal gas. And the way the Otto and the diesel cycle problems go is that this pressure and temperature often are given. And so you can calculate V1. V1 is equal to RT1 divided by P1, isn't it? Just using the ideal gas equation. And then usually they give you the compression ratio. So what is V2 equal to? V1 over R. V1 over R. And then how do I calculate maybe T2 and P2? There's a number of ways to do it. Maybe you want to use that isentropic expression with constant specific heats. Maybe T2 divided by T1 is equal to the volume V1 divided by V2 to the K minus 1, which is the compression ratio to the K minus 1. So the higher the compression ratio, the greater T2 will be over T1. Okay, that's how you would calculate T2. Similarly for P2, P2 divided by P1 is equal to V1 over V2 all to the power K, or the compression ratio to the power K. So you're jumping back and forth, getting these pressures and temperatures. Either they're told, you're given some information. A lot of times they'll say, oh, the maximum temperature in the cycle is, well, that's T3, if they tell you the maximum temperature of the cycle. Or the amount of heat added is so many kilojoules per kilogram. Go back to the first law for the process 2 to 3 and then calculate T3. But you want to get these U's as a function of temperature, then calculate the Q's and the W's, and away you go. How about same thing for the Brayton cycle, okay? Let me do this. Let me go ahead and pause and see if you have any questions for me. I know that's a lot that I tried to cover. I tried to cover it, how do I call it, conceptually? But I think if you get a good conceptual roadmap out of all these 3 cycles, then it's just filling in the details. Somebody will ask me, what is the cutoff ratio again? Is there a cutoff ratio for the Otto? Is there a cutoff ratio needed for the diesel? Yes. Is there a cutoff for the Brayton? Only for the diesel. And what is the cutoff? Cutting off the diesel fuel at constant pressure heat expansion. All right. Well, thank you very much for your attention. We'll see you later.